Okay, so the first talk is by Hermann Sierra. We'll talk about tensor networks and CFTs.
Yes, okay. Well, I want to thank Ignacio and Frank. You are now to be part-time gratis. So for the nice invitation to come here to this interesting workshop. So the topic of this talk is going to be tensor networks, states, and homomorphic theory. So the aim of this conference is the common topic is tensor networks. That you all know what they are. It's a kind of general technique to propose answers for the ground state and low-lying states of many body systems. Right? That's the general idea. These ground states will be, or low-lying states will be for Hamiltonians, usually lattice Hamiltonians, which are short range. So being short range will mean that these states, these ground states, okay, will have some properties, and the main property is that in general they will satisfy the so-called area law. So when you make a bipartite system, you split the system into two parts, real space, the entanglement entropy will follow this law, area law, we call area law, or perimeter law, or, which has some deviations. There are logarithmic, for instance, deviations in 1D. And these deviations we understand very well because they are come from conformal theory. Okay, so in 2D, for fermions, there are also logarithmic deviations. And the general idea is that there is this area law. And this area law is what identifies kind of corner in the Hilbert space of your system, and this corner is what you want to describe using these tensor networks. Okay? That's the kind of the ideology, okay, of this method. So conformal theory is something else. Okay? It has been introduced in physics in many places. Originally, it came in string theory. So when people in the 60s invented string theory, so later realized that there is the theory behind are strings, static objects, and the field theory was conformal theory. That was the first place where conformal theory have a role. I will be talking about 1+1 conformal theory. Okay, one space, one time, or Euclidean will be two space. Okay? So next place was statistical physics in 2D. Okay? There, the critical phenomena are also associated to conformal theory, described by conformal theory. So was this important paper by Belavi, Polakov, Samlochikov, who introduced the general setup of conformal theory in 2D critical systems, intimately related to conformal theory, in string theory. But then appear also on this matter. On this matter, the work by Haldane and others, they find out that in one dimensional critical systems, you have the Latimer liquid. The Latimer liquid is nothing but a conformal theory. A particular conformal theory. Okay? So they are also playing a role of conformal theory. And another place where it has a role is in the fractional point-to-call effect, actually. Conformal theory is kind of technique that people used in the past to propose answers for the Lofley wave function, Moore-Reid wave function, so on and so forth. So there is also an important role. Also, inter-Simon theory is also related to conformal theory. So you see, it appears in many places. So here, this is just another application of conformal theory to tensor networks, which in fact is correlated to the idea of the fractional quantum-Hall effect. The way conformal theory is applied to fractional quantum-Hall effect is what we will be doing here. It's basically the same idea. So let's then go to the beginning. Well, I thought that it would be nice to kind of refresh how metric probable states and PEPs were introduced by Ignacio and Frank. Okay, it was kind of interpretation of LPS in using quantum information idea. So let's remember this is quite elementary. So there are two ingredients for the LPS that also apply for PEPs. But the first idea is that you start from a pair of states and you construct a state which is maximally entangled state let's say, two sides. So alpha is the auxiliary index. Okay, so you have a bunch of maximally entangled states like that. So that's the first ingredient. Then these alphas are the auxiliary indices. Or ancillas, like this. Okay, that's the first element introduced. Next, you have to make contact with the physical indices. So you will introduce a projector like this. So you take two auxiliary indices, alpha and beta, and then you do a projection to the spin. So S will be this is the S spin, I call it a spin, but this is the physical index in general, which can take a discrete number D values. Okay? And chi, this chi is the number of auxiliary indices there. So the construction goes by putting a collection of these maximal entangled pairs and then doing a projection for every of these pairs. Where you put the auxiliary indices, the spin indices, okay? So, and this is nothing but the DS. Okay? This is the matrix product, this is the way you have constructed. If you add, so this is what we call psi, and then becomes the product of these matrices over the internal indices times the given product of the spin states. If you add more indices like that, okay, then you get PEPs. So PEPs will be the 2D version of that. So this is how Ignacio and Frank introduced the PEPs, which in a way is very similar to the AKLT. Right? This is precisely the way they did. Okay, now suppose we take this auxiliary space, index alpha, which is finite dimensional, and suppose this is infinite dimensional. So you want to think of alpha as an infinite dimensional object and actually as an extended object that we may call a string. So the different internal degrees of freedom are, let's say, the different possibilities of exciting a string. So now let's translate these two objects in this language. So the first object will be something like that. So it will be like a string propagating in the space-time, okay? And in fact, this is what people call a propagator in the string theory, okay? So this is our maximal entangled state. While here, for the projector, you will have to take, say, one string here, one string there, and to put the spin object over there. So this will be the projector. So the projector is kind of, it's a vertex. It's a vertex object. There is a string coming here, there is a particle, sort of a particle coming there, and then another string coming out. So this is a vertex operator. So these are the two ingredients, okay? If you think of the auxiliary space as an infinite dimensional space, and actually as a string. So this is a vertex. Well, these are the two ingredients that people use in string theory to construct any process, any scattering process. For instance, when people did in the past, they have particles coming in, and this particle will be photons or whatever. So that was the picture. So using this, you can decompose that scattering process. You can split it using propagator and vertices. So in practice, this is much simpler in our case. What we are doing is simply our wave function is putting together propagator and vertices, and as from this feature, that's simply a correlator. A correlator of some operators. So this is the what you get at the end. So let me say it again. So this quantity here, you can think of A is alpha beta, which in MPS we represent like this. Now this becomes an operator of the given bit theory. So this will be an operator of conformal theory. So this is what we are basically doing. We are replacing matrices, finite dimensional matrices, in the internal space simply by operators in conformal theory. It's very convenient to use a type of operators which are called primary field. So at the end, the wave function that one proposed is simply the correlator of a product of vertex operators, or primary fields. Okay? That's simply the idea. So now you see this is really realize the idea of having this chi infinite dimensional, but not any infinite dimensional object will be conformal. Okay? Only the ones where these objects are operators, are actually primary fields. Yes?
I thought this, if you combine these two pictures, you get these operators on the torus rather than field.
Yes, well, in that sense, you can play with several topologies. Indeed, torus will be one. This, for simplicity, I will take the sphere, but you can also play with the torus. Indeed, and higher genus, actually. So this nice, well, geometrically it's very nice, right? Because you then can picture the state as a Riemann surface where you have inserted the operators. Okay, so this is where you put the auxiliary values. I mean, the auxiliary space is really the string per se. Okay, that's from this point of view. Okay, so why this is interesting? Well, for several reasons. One is that you will make contact with interesting wave functions that have been studied in the past. In particular, we will contact, in 1D, we will contact with so-called Caldensastri wave functions in 1D, and in 2D, we make contact with wave functions that appear in the fraction of quantum effect. Okay, so this is kind of general setup where you can go to 1D, 2D, and actually see that the 2D wave function is just coming from 1D. I mean, you can make all kind of analysis. Another interesting thing is that conformal theory has a lot of symmetries. I mean, depending on the conformal theory. In particular, when we deal with the best of with the models, there is huge symmetry there, infinite dimensional. So we can try to explode that symmetry to our purposes. So we can construct parent Hamiltonians, we can find correlators, so on. So depending on the given conformal theory, we can actually explode all these symmetries. Okay, so let's start with this example. That we working with Ignacio. Actually, I forgot to say that this is well known with Ignacio, Dirac, and Lipsen, and also more recently with Conformal. Okay, so this is a series of papers work in collaboration with Ignacio and Conformal. So the first example is simply, let's take the simplest conformality theory, which is a free boson, massless. So this is the simplest conformality theory you can have. I will take it to be chiral, so I only take the chiral component of the boson. This theory has central charge equal to 1 and appear in many places. So this is the simplest conformality theory. With that, we can construct, let's see what is this operator, AS. What can we choose for AS? Well, you can choose, for instance, the exponential of this object. So these are called vertex operators. Okay? So we simply take the exponential. Where do we put the S? S will be the spin degrees of freedom. I just take spin 1/2. So S, let's say, is plus or minus 1. So this is the physical degrees of freedom. So we put it there. here we have the freedom to put a constant, so I call it square root of alpha positive. And here we have the chiral field. Okay? So these are the vectors operators. Still there is the freedom of having a number here, Ks, which for our vectors will be a sign, plus or minus. So this is the answer. This, as an operator, you want to represent it with the infinite dimensional matrix, because you have to consider all the oscillators. The field phi has an infinite number of oscillators, so this is an infinite dimensional matrix, okay, in the space of oscillators. Okay? Fine, that's very well known. And now the rule is...
Question?
Yes.
Can I ask you, so is it countable infinite?
Sorry?
Is the
It's
infinity
countable.
countable?
Yeah, yeah. It's a bunch of oscillators. I mean, the only one detail, the conformal, this is a primary field, meaning that has nice transformation properties. And the conformal dimension, or the scaling dimension, is the square of this number divided by 2. The square of h is 1, so it's simply alpha over 2. This is the scaling dimension of this field. Now, you compute what will be the wave function. So the wave function, according to this rule, it will be the expectation value of this product of operators on the sphere. This is computed on the sphere, not on the torus. Okay, we can do it on the torus, but let's do it on the sphere. So now this is very simple to compute. I mean, this has been known since long. So first you will have the product of all these numbers, and then here is simply it's a product of monomials. So this is the general rule for this expectation value. But there is a condition here. This theory has a symmetry. The action, you look into the action, there is a symmetry that you can translate the field phi by phi plus constant. So there is a U1 symmetry here. It means that when you compute the correlator, if you do this, it must be invariant. But if you do this replacement here, you will get something like e to the sum of the spins. But this must be 1. So this is only true if the sum of these quantities is 0. So the correlator is only non-zero if the sum of the spins is 0. And this is coming from the U1 symmetry, okay, of this theory. This is charge neutrality, what has many names, but that's the condition you have to read. Okay, so okay, this is an answer for a wave function of a spin system with the spin 1/2, which depends on alpha and these coordinate sets. These are your variational parameters. Okay, and now you go and see what. Let's try to apply this to some Hamiltonian.
It's a quick question again.
Yes.
I don't know much about. So from the expectation value to this line, is it clear how do you go from?
Yeah. You just plug in this here, and there is a general formula for getting the expectation value of vector operators.
Okay, but it's not something I should be able to see without knowing.
Yeah, no.
Okay.
You have to. Yes. Well, this was known long ago. String theory already used that. It's very simple to do.
Is that Giancarlo Big by any chance?
Sorry?
Is that the Big brother? No.
Big theory.
Well, you can do it several ways. This you can write it like you split it into creation and inclination operators, or like that, and then you use this can by Hausdorff formulas. So there are many ways to do this. Using operator formulas, or using path integral, or many ways. Because the theory is Gaussian, so you can do all this. Okay, so the moment you can try to check it, apply this. We applied it to the anisotropic tensor space. So this is a place where you can apply this Hamiltonian. So that Hamiltonian, well, you know very well, is this is the Hamiltonian with take it from, so we have a speed chain on a, with any boundary conditions inside, and then this delta is the anisotropy. So delta 1 will be the isotropic Heisenberg model, antiferromagnetic. Okay. So that's the model that is solved by the tensor. Okay. Some people know very well this. And now now you want to see, well, try to find if this wave function over there is a good variational answer for the ground state. Okay. So that's the idea. But let's say one thing first. What is the phase diagram of this model? Well, let's put here delta. So when delta is between 1 and -1, this model is critical. So it's gapless, and it is described by C equal to 1 conformal. In this region, the ground state is ferromagnetic, and from here there on is antiferromagnetic, and this gap is a gap. So now let's try to see if this wave function with log is a good answer for this ground state of this system. So the Hamiltonian is tangentially invariant, so let's make the guess that the wave function is also tangentially invariant, and this means that we can take the set coordinates on the unit circles. So like here, they are mimic of the positions of the sides of the spins. So we take the sets to be e to pi n divided by n. Now this is an answer. Okay? We could choose other, but assume that the wave function is tangentially invariant. So we are left then with there is the skies, the signs there. This. So the Ks, we can choose them following what is called the Marshall sign rule. Marshall sign rule is that you can justify. That is something like E pi is A plus 1 divided by 2 if A is even, and 1 if it is odd. This is called the Marshall sign rule. Marshall sign. Okay, so then this is the sign, and then we are left simply with alpha. So alpha is the only variational parameter that you have. Now we just do variational. We compute the expectation value for the Hamiltonian, and we minimize. And find alpha. Alpha as a function of the isotropy. Right? That's the rule. Okay? This is a variational answer, so fix delta and then find alpha. So what we find is the following. If alpha 0, delta 0 is basically that interval, so this alpha takes the value of 1.2. When this is -1, alpha is actually 0, and here is 1. The clear thing is that in these 2 points, alpha 0, alpha 1.2, this wave function is the exact ground state of this Hamiltonian. It's exact. So these 2 results are exact. And you can prove it. You can prove it because this point is a Harper-Boson, the wave function is later determinant, and actually you can map this later determinant like this wave function in a race for alpha 1.2. If we go to the case alpha 1/2, well, here with delta 1, here with this value, which will be very, very interesting. Now, you can also check what we did to compute we say here that the theory is critical. So you can take this wave function and compute the Rayleigh entropy. Rayleigh entropy. So let's compute the Rayleigh entropy. So you compute this quantity, Rayleigh 2 because it's easier to do numerically, and then conformal theory tells you that this will behave like this. This is the formula from conformal theory. And from here you reach the value of C. But indeed, you find that in this regime, the wave function have C equal to 1. Okay? Depending on alpha, depending on where you are, there are oscillations. When you plot the oscillations, but in average is 5. Okay? You get C equal to 1. So this is a check that this wave function is really described in a conformal theory with C equal to 1. If you go here, well, you do the same computation, you see that the entropy saturates. So this is the area law. So you expect the wave function to describe a capped system. Okay? Well, indeed, this is in this region there is a gap. This is the antiferromagnetic region. So actually there must be another function, alpha, as a function of delta, in this region. In general, there is a case for that. We have a case how alpha depends on delta. Well, it's something like delta is minus cosine 2 pi r. So when delta is in this region. So you can even make a guess what would be the relation between delta and alpha.
This is another alpha, right?
Let's say alpha.
Same alpha was equal to...
Yeah, for instance, alpha 1 half.
Same alpha.
This will be cos pi, which is 1, and then 1. Right?
Phi.
Sorry?
What is phi?
Pi. Here.
Phi.
Pi, well, it's just 5.
Phi.
5, sorry.
Phi.
Okay, pi is here, this is the free boson.
So that's like an arbitrary function.
Well, it's the field, it's a field. It's a conformal field.
Mm-hmm.
So it's something like, there is a zero mode, the momentum, load set, and a bunch of oscillators here. It's something like that. You expand in oscillators. Okay? So it's a field, conformal. Okay. So this is what you get. So physically you understand that this rate phi, that this is a critical region, and then this is a half region. Yes.
So it's, I think this result is very spectacular. You have a variational wave function down there that gives you just one variational parameter alpha, whereas you add the extra ansatz that the position are determined on the circle.
Yes.
But is there any ingredient? So I was trying to think, okay, let's start with that wave function. Let's forget about the first 20 or 15 minutes of talk, right? Let's start with that variational wave function. We apply it to that system and we get very nice energy. So is there any place where you need to go back to the MPI representation in these calculations? Could you just start with that variational wave function and apply? You know, is there any MPS structure that is relevant to the calculation? Or the MPS is part of, admittedly, very nice story how to get to that wave function.
Okay, well, let's see. We want to do something else, for instance, right? For instance, the parent Hamiltonian.
Right.
There, for instance, we will need to know that, right?
I see.
For instance, right? I mean, it's not that here it is, the wave function, and now go and compute something. No, let's try to do more, right? In particular,
and then the MPS structure will be relevant.
Yes.
Okay, I see. All right, thank you.
Yeah, good question. Well, let's try to do what I said in the case we can. Well, we can tell this, but in this case we can continue and explore these properties is when they are more symmetry. Actually, one case is where there is more symmetry is precisely when alpha is 1 half. When alpha is 1 half, this is the case that corresponds to delta 1. Delta 1 is the isotropic case. So here we have issue 2. The space A have issue 2 symmetry. So you may expect that the conformal theory will have also a lot of symmetry. Indeed, in this case, these operators have this one. Just for this alpha 1 half, remember this was like square root of pi. So the operators now take this one. This theory has already an operator which is a symmetry, which is the derivative of the field. The derivative is
I'm kind of confused. So this A of S is A of S and Z, isn't it?
Yes, yes.
So it is a. How is this countable infinite?
Okay, suppose you take a basis, we have to choose a basis of this. The basis will be like these oscillators to powers.
You could have.
So this will be the irregular space base. This is a focus space. So you create all these states by acting on the oscillators creation to powers and multiply all possible oscillators. And then there is the zero mode characterized by sign charts.
So you kind of have a lattice.
Yeah.
No, there's no lattice in momentum. It's vector if the functions are very well behaved.
It's like
Fourier transform.
It's a field.
these are the Fourier
mode.
modes. These are the Fourier modes. So the Hilbert space is a focus space. And the base of oscillators, an infinite number of oscillators. This is why it's understood.
Continuous function is determined by countably many function values.
Okay, so take this, and here is a U1, but also you notice that these operators, these two operators also connect and mix this. You apply, you got minus I square root of 2, you apply plus, and then you get another one. So these operators generate a symmetry. You can correct it. These two operators are like plus or minus. And these are like S plus and S minus. But the conformal dimension of these guys are the square of this number divided by 2, so it's 1. And this is also 1. So this is, in this case, for that value, these fields can be related by these other fields. And these other fields are currents. Currents are operators with conformal weight 1. So they form actually an algebra, which is called SU2. The barricade, which is actually a rest of with the model. So just for this case, the conformal theory increases and becomes very huge and described as SU2. So what you discover then in this case is that these fields.
This S plus minus, you mean speed, raising, lowering operators
Yeah,
locally?
yeah.
But like S plus square kind of equal to 0, no?
S plus, S minus, well,
S
these are the
plus
0.
square is equal to 0, right? It doesn't
Zero.
fall to the left side.
No, these are the 0 mode for these operators. Right? That's what they are. Sorry?
Should I think of this as a raising operator on the side or on the
Yeah,
chain?
On the side.
it's
The translation.
momentary space. It's momentary space. So you have to think of this. Now they become this. They are like currents, it's plus or minus, but depending on the position. So you would have one of these operators, then this. And then there will be a 0 mode, which you can expand. You can do a Taylor expansion, and then you will have an infinite number of modes. Okay? So this is how, for instance, the Hamiltonian tensor, conformal theory is the Hamiltonian tensor. Okay, so these are similar things, but associated to internal symmetries. So this is how you discover a huge symmetry in this theory, just for that value, which is maybe not surprising because the spin chain have SU2 symmetry. And this is a particular realization because there is this extra labor K, which in this case is 1, but in general K can be any integer. So it can be 1, 2, 3, so on. So when you have SU2 symmetry in the conformal theory, you say that there is SU2 labor K. It's called labor. So here we are finding that the label is K. The label fixes the central charge of the theory. So of any of these conformal theory has central charge. We claim K plus 2, which for level 1 is precisely 1. But 1 is also the central charge of the free boson. This is why SU2 level 1 can be bosonized. So because the central charge is 1. Okay. Later we see examples with k equal to 2. K equal to 2, C will be 3 cards. Okay. So then what we are finding here, the other important ingredient is why we have all of these theories. These theories, I told you that they have primary fields. But this is a theory which are called rational homomorphic theory, meaning that there is a finite number of primary fields. Okay? And this is why you can solve actually the theories. And the number of primary fields here, they're classified by the third component of the spin, which can take values 0, 1/2 up to k over 2. In k equal to 1 means that there is only two primary fields, which is 0 and 1/2. 0 is the identity, this is one primary field, and the other one is 1/2. Then what we discovered is actually that this conformal theory is, this wave function that we wrote is just the conformal block associated to this primary field. There is only one non-trivial primary field, apart from the So this gives a complete interpretation of this model, which is we are using as a wave function the conformal block that you can construct with the spin 1/2 primary field, and which is unique. So this wave function is the current of this. So this is what you're left with here. And this tells you, well, this kind of particular case, at this tells you what is the general rule now. Take any conformal theory, take the correlators of primary fields, and construct a wave function. Okay? Then from there, you will have an infinite number of models. Okay? Then using all the symmetries of the conformal theory, you will be able to construct parent Hamiltonians, etc. But this is the message. Okay? Use conformal theory to propose wave functions for these systems. So in this particular case, let's go back again to this example. This wave function that we found is called the Hamiltonian wave function. Okay, well, what is the wave function? This wave function? Well, suppose you take again a unit circle with n sides, and now let's make additionally. So suppose spin 1, spin up is empty, and spin down is occupied by a hyperbole. This b squared is square 0, so this is a hyperbole. Then we will take this system with total third component of the spin 0, total, which from this point of view is half filled. So half of the sides will be empty, and the other half will be occupied by the hyperbole. And then you label the position with little m. And there will be a half of these little n's. So the wave function written by Caldet and Sastry is this. So it's a wave function for an spin 1/2 system, but written in a hand proportion values. Okay, it's a clean straight, but this is what it is. What is interesting is that you see this part here looks like the wave function for roughly with filling fraction 1/2. This is what it is. Okay? You have these monomials to power square. But instead, where you have an electron, here you will have to think that there is a spin down, while the empty sides correspond to spin up. And there is also this extra factor here, is there to guarantee that this is not only first component 0, but also the total spin is 0. So this is a sigma. This wave function is a sigma. Well, the way Haldane and Sastry got it is interesting. It has to do with a Goodwille projection for previous step. The question they ask, well, here it is the nice wave function, but what is the parent Hamiltonian? Is there a parent Hamiltonian for this? But they found one, K4. So it's an spin, change Hamiltonian, but all the spins are coupled, and the coupling constant is the inverse square of the distance. So if this is the distance between this spin and that spin on that side, so the exchange coupling goes with the squares of the distance.
This is the sine square.
Yeah, this is the sine square of the angle. Yes. So this is the Hamiltonian. And there is also another interesting property, is that the correlator, the spin-spin correlator, in this state, there is a sub formula for that, but actually, if you do asymptotics, this is a sub formula like that. So if this spin is position n and the other is position 0, when n is large, it decays like algebraically. There is a term which oscillates with the power n, and the other with the power uniform term, which decays like 1 over n squared. So this theory is this theory that the theory is conformal. Okay, with algebraic decay. While in Heisenberg you do the same computation for the Heisenberg wave function, it's the same thing, but here there is an logarithmic correction. And this is the same. So Heisenberg is also is conformal, but it's not at the right at the fixed point. It's not quite at the fixed point. There is a logarithmic correction.
Also high corrections, high powers of n.
It's a higher power, yeah. And the reason is that Heisenberg model is a marginal irrelevant perturbation of the homology. And this marginality is what produces the logarithmic correction. Well, and this Sastry is sitting right at the fixed point. So that's a very nice problem. So now you ask, well, what is the relation? What is the relation of this formula with the one we got before? Well, look pretty similar, but there is the wave function we know is there is this product of spins. Okay? So how we go from one to the other? Well, we go simply through this map, because the spin up is 80 side, spin down is 5. So you may write this is the correspondence between the spin and the occupation number. So if the spin is up, so it's 1, n is 0. So n, I call it 0, it is empty. And if it is minus, then it's occupied. So there is this simple formula. Now you go here and replace that expression, 1 minus 2, we call it u. You replace over there, and now from here, when you got the product of these q's is 4 qa divided by 2, so it's 2qa qm. When the q's are 1, if the site is occupied, so this 2 is present with this 2 here. And there are the cross terms which combine with a sign here, and this gives you this. So there is a simple way to go from one to the other. So this is why it doesn't look that we are dealing with Sastry. Fine. Now, we said that this is a conformal theory an interesting property is that these theories can be solved directly because something are called null vectors. So in the representation theory of these conformal theories, there are a lot of conditions that you can impose. They are natural to the theory. In particular, the system of null vectors. But what is a null vector? Well, suppose we got this primary field with the spin 1/2, which there are two of them, up and down. So this is the primary field. Primary field sits at the top of a tower. You get the rest of the tower acting with this mode, with the currents. With the modes, with the currents, you generate the E3 tower. The first step, you will add with this operator, mod -1, and in general you will have here two multiples. One with the spin 1/2, and the multiple with spin 3/2. That's the generic situation. Generic in the meaning that whenever k is greater than or equal to 2. But for level 1, this multiplet is not there. So there are 4 states which vanish when the level is 1. And these are called null vectors. So in the representation theory, you have to kill these null vectors. This killing is precisely what makes the theory integral, and why you can solve the entire theory, the conformal theory. But in practice, this implies the following. If we got the conformal law, we got the wave function, from that condition, that this vector shouldn't be there, you can derive a bunch of algebraic equations like this, where these C's are so, and this so this is the consequence of having one of these null vectors. That there is a bunch of operators, one per side, and one per this A, that annihilate the wave function. You see, this is an enormous amount of equations that annihilate your state. Okay. Now, you can construct, for instance, that operator with the sum, with I and A, and you call it H. This is a positive, the semi-definite operator which annihilates the wave function simply by construction, because you have proved that the C's over C are 0. Then you have found that H
This
is
C capital has subindex I. Where is this subindex I in the right?
I is the lattice side.
Where is this in the right?
Here.
Okay.
Yeah, here and there. Yeah, there, over there.
Okay, I understand. Thank you.
So then we just constructed a Hamiltonian. So this is a parent Hamiltonian for this wave function. Now, if you take the positions, the sets, to be the unitics, equal space, then you discover that that Hamiltonian is precisely the Hamiltonian Hamiltonian. So this operator is actually H, minus and constant. So the parent Hamiltonian, by Hamiltonian, you can construct it with these two vectors. But now, in doing so, you can consider situations where the sets are in any position. You see, you can be equally distributed, or can be even in 2D dimensions, in 2D. So there is a general rule, okay, to construct the parent Hamiltonian. It's just in one case, when it's uniform distribution, you recover the Hamiltonian. Okay, so here is why you're using the structures, right, of the conformal theory.
Two good questions.
Yes.
So is there a reason to a priori assume that you always build a Hamiltonian that's frustration-free? Because this construction gives you a frustration-free
Yeah, well, it's not unique. You can add more constants. Yeah.
But the Hamiltonians you build, is there a reason to assume a priori they should all be frustration free?
No, not necessarily. But this you just look for a parent Hamiltonian, right? So you have to check. Maybe there is some other solutions for that. Maybe not unique, but you can solve it unique. Right? Taking some limits and.
But it's not local, so it's not the non-local frustration free. So it makes a difference from the usual case.
Yeah. Yeah, indeed, it's not local because it has all kinds of countries, but it decay very fast, okay, including. Okay, so this is, so that's the general idea. For this, not only you get the parent Hamiltonian, but from this type of equations, you can write equations for the 2-point correlators, for instance, and from there you can solve analytically and find this result. This result can also be gotten from that. And you can also construct 4-point correlators and so on and so forth. So, and we did actually so this bunch of equations, linear equations for correlators, coming also from this decoupling equations. Okay, so this is how you construct this spin workup, level 1, but let's take, now you can go in several directions. Let me describe the cases.
So what does it model? Like what does this Hamiltonian model? Like what is underlying?
Yeah, well, it's kind of, as I say, it's like a version of Heisenberg. Right? This Hamiltonian is like an improved version or a piece-point version of Heisenberg. Hamiltonian spin. This is what is model. Okay? And the way we construct it, you see, we started from the anisotropic chain. This was the isotropic point. This is SU2. SU2 is actually conformal theory, SU2 equals 1. And now this is like the perfect Heisenberg chain. This can be a Sastre chain. But then, suppose now we take possible generalizations. Well, one is to go higher speed. Higher speed is one possibility. So how to construct spin 1, for instance. For instance, spin 1 we take SU2 level 2. Here the primary fields, there are 2 primary fields, 3. One is the identity, but this doesn't fit in this model. And there is now the possibility of having a spin 1. A spin 1 primary field. So we simply take the wave function is a product okay. So now you can make an answer for the spin 1 wave function using these primary fields. What it is? Well, you can show that these fields can be plus or minus 1 and 0. The plus or minus components, you can represent it again using a tree boson. Well, the 0 component, you can use a Majorana term. So this wave function becomes a product of these vector operators, which then give you this kind of factors that we already solved. And then the positions where the speed is 0, the component is a correlator of Majorana fields. But Majorana fields gives you a pattern. So this is the wave function for, in this case, for the speed 1. It's a product of these monomials, kind of just a wave function. But now, you get a pattern. Wave function.
What's SI in this one? S sub I?
Sorry?
What's S sub I?
SI are these components, which can be plus or minus.
For the ground state wave function, they should
Yeah,
be
this is the ground state wave function. This is the ground. Okay, so you can construct there is this wave function, there is the Hamiltonian. You just construct using these new vectors. So you begin new vector, then we have this form. And you can actually see what is this is a conformal theory. So what will be the C? The C that you get is actually we have. So I think that we do the computation, we do compute the Rayleigh entropy, and for this wave function, the C is actually 3-half. So this kind of bootstrap, we use a conformal theory with C 3-half, and then we get back to the C 3-half. Okay. So, but here you can also use the spin 1/2 field, and that's more interesting. The spin 1/2 field has non-trivial fusion rules. So in particular, 1/2 is 0 and 1. So when you construct a wave function as a product of the spin 1/2 fields, then there is not one wave function, there are several wave functions. And then this is a situation where the ground state is a manifold. And how many states you compute them using fusion rules. But again, you can use the U vectors and construct a Hamiltonian, which is, has a ground state which is degenerate. So again, there is a Hamiltonian with a degenerate ground state. And the degeneracy is given by the fusion rule. Okay. Well, there are another possible generalization, which is going to higher dimension, equal to 2. Well, here we go again to Instituto level 1. Well, the wave function is the one we got before. Exactly the same. But now we take the sets to be on the square lattice. And we want to try to do this in the hardcore Poisson basis. Before, you remember we got this factor, which caused this Halden-Sastry, but then there was an extra factor that combined it with the sign here to give a thing like that. But now, what is happening in 2D is that what we are getting is a Gaussian. So this is the factor that before was not that important. Now in 2D is producing a Gaussian. So now, as I said, this is a wave function, this is a known wave function, which is a lattice version of the Philip traction 1/2 of bosonic. It's a bosonic rounding state that we get in the limit where the square lattice is large. So it's not that you got the Gaussian right from the beginning. No. It's when you take the lattice big and then this extra factor gives you the Gaussian. So this is how we make contact also in 2D with this wave function, which is due to Parmenier-Laville. Which is one of the cases that wave function which corresponds to a spin liquid. So we check several properties of this spin liquid, like topological entropy, correlations, and well, several other properties. Again, here we can construct a Hamiltonian, a parent Hamiltonian. The novelty, as compared to the Halden-Sastry, is that there is an ester, is a free body coupling. It's a triple product of 3 spins that was not in the 1D version. The 1D version there was no free body Hamiltonian. But here it is, because this Hamiltonian breaks time reversals, and the wave function breaks time reversals in 2D. So this is coming out naturally from the construction. But this Hamiltonian is not realistic because it's not local. There are a lot of non-branch couplings. So what we did was a truncate that Hamiltonian to Linus neighbors. We did a truncation, only keeping next to Linus coupling with a three-body pair, and they check things like that Hamiltonian. You can compute the numerical in the ground state, then you do overlap in the conformal field theory wave function, you investigate how good is the overlap, but the overlap is used to be very, very good. Around 10 or 20 sites is like more than 99%, 97%. Then we check several things, the generality of that Hamiltonian, that is topological, so on and so forth. So you see the general recipe here is that this kind of wave functions coming from conformal field theory, well, it contains a lot of structure, is a guide to see, to explore the topological properties, and from the pairing Hamiltonians you can make truncations and hope that in the truncation you stay in the setting beside the glass. And then you can do things like overlaps and to verify if the wave function is close to the wave function. Well, I think this is, thank you very much.
Thanks a lot. Questions? Yeah.
So in this construction in 2 dimensions, if you follow back to the original tensor network motivation, then you would end up with a PEPs with infinite bond dimension. Is that what you would have?
Yeah. This is what you will have. You will have, I add with a PEPs, with infinite dimension.
I don't understand the topology of the manifold. So
It's an MPS, no? It's not
Sorry?
PEPs. It's not a PEPs, it's a matrix product state, I guess.
Well, it can be viewed in 2 ways.
but
It can be viewed, in principle, it looks like MPS, right? Because you multiply the vectors. But if you look into the positions of the vertex operators in the surface, you will be able to cut it.
But this surface, this surface is sphere, or is this
A sphere.
It's a sphere.
A sphere. Sphere. So the difference is simply that. So in 1D, we can actually use this for the vertex. I'll put it here, right? Here is where you have the primary focus, the layer, right? In the unit circle. Now this is the origin, so you can cut this like that. Now you can the field configuration here is like alpha, and another field configuration is like beta. And here is your field. So the A alpha beta is can be seen like this. There is a field here and the field configuration there. So this is a MPS, right?
But do you identify
Well,
infinite with zero
sorry?
or not? So the MPS would come naturally, I think, if you were on the torus.
Well, torus will be a little different. No, but let's talk about the sphere, right?
Right. What
And
I'm
now,
saying is,
if we go to 2D, we will have things like this. This is what we will do. So here you will cut like this. Okay. So the MPS, I mean the PEPs will be this order here, with 4 sides. So the field configurations here, this will be the A, alpha, beta, gamma, delta, AC. This is how it works. Yeah. So this is looks like a PEPs, APS in 2D also, but if you were to do it very properly, you will see that there are actually 4 sides around. So this is likewise a PEPs. On the torus. Now we can do it on the torus. Well, the torus.
no, I was trying to relate this to your original picture where you had the strings.
Ah, yes.
So if I want the strings, do I need to work on the torus?
No.
No. So the strings are open strings in this case?
Yeah, in this case.
Okay.
Yeah, we're using that to.
Okay.
But this is a better picture.
For the 1D chain, how do you interpret like the central charge? Is this something that you can interpret as an entanglement measure of something?
Yeah. Well, the C will appear in the entanglement spectrum, in the entanglement entropy. Right. This is how the C
The
enters.
entanglement entropy will be what, scales of log of system size
Yes.
with coefficient C?
Yes. Yeah, you will have the typical formula from conformal theory. You split the system into 2 parts. Right. So there will be something like symmetry, log n by pi, sum pi n over a. you take this wave function, do this splitting for the finite size, and then the entropy will be like that plus oscillation. If there are oscillations.
Is that a sign of pi wave?
Sorry?
Is that a sign inside?
Sign, the sign. Yeah, this is the finite size formula for the entropy. Finite system, this is the finite. This is a finite size formula for the entropies.
But if sign becomes negative, then all of
No, not negative. Well, this is pi over n. No, this is always less than 1. No, it's okay. It's, not less than 1. This is less than 1, but this is bigger than 1. It's positive.
so your n is always less than n over 2.
Yeah. Yeah, these are the formulas by Vidal. Well, it was a joke. I mean, by well, yeah, before by Wilczek and Jose. Yeah, these are the typical formulas.
Does this formalism allow you to easily apply wave function renormalization to, for example, this Haldane-Sasti model and see that indeed it is the RT fixed point?
Yeah, no. Well, yeah, I think you can do it because the RT will be the operator product expansion. This is how you will implement RT. You will take a bunch of sides. Yeah, actually that will be interesting to do because it will be a way to see how this relates to Mera, for instance. Because the Mera actually is a way to do RT, right, in this picture. But here, this is already conformal. So there should be a relation between them. Yeah, indeed.
Okay, so maybe we shouldn't risk that the coffee gets cold and maybe postpone discussions to the break.